So previously we've looked at buffers and how a buffer works. And now what we want to do is we want to look at how do we actually calculate the pH of a buffer solution. Now reminding us that a buffer solution is a weak acid and its conjugate base, or a weak base and its conjugate acid, right? So we have significant amounts of each of those. So we're going to be able to, once we know how much we have of each of those things, calculate the pH knowing how much of a weak acid or a weak base we have present in the solution. Also being able to calculate how our pH changes as we add in a strong acid, and how our pH changes for this buffer, and how we add in when we add in a strong base. Specifically focusing on what kind of neutralizing reactions do we have that are going to neutralize our base or acid when they're added into solution. Now, when we're using a buffer and identifying how the pH is changing or what the pH is, we have the ability to use a magnificent tool, the Henderson-Hasselbalch equation, which is telling us that we have the pH of our solution is equal to the pKa of whatever weak acid we have in the buffer, so our buffer weak acid. And to that, we're going to add the log ratio of the concentration of our base to acid, or the mole ratio of our base to acid. We notice we can use these interchangeably, and we'll talk about why we would possibly choose one versus the other. So let's first look at our first buffer that we have here and talk through some of the applications of this. So what we're told is that a buffer was prepared by adding formic acid and potassium formate. So here we have a weak acid. It's good to investigate what kind of solutes we have, a weak acid. And then this is a salt that contains potassium and the formate ion present in solution. Just for simplicity's sake, I'm going to write HA and A minus now for those to simplify rather than having to write the whole structure out every single time. And we're told that this was done in a 2-liter solution where we have a certain concentration of our formic acid and a certain concentration of the formate ion with our potassium formate. So important thing to notice is that we have a pretty good amount of each of these, or similar concentrations of each of those. And that is a good hint to us that this will be a buffer solution, even though we are already told it's a buffer solution, but that's because we have similar concentrations of our acid and our conjugate base. Okay, not the same, but similar enough so that way we can see that we're going to have similar amounts of those and significant amounts of those. So the first thing we want to do is identify just the pH of our buffer. So it is a buffer. We can use pH equals our pKa value plus the log of, again, we could use the molarity or mole ratio. Well, since we already have these in molarity, let's go ahead and just look at the ratio of our concentrations of base to acid and be able to identify our pH there. So here we would have our pKa, that is for our formic acid, and we can go to a table, we can find the pH, and then the pKa, which would be 3.74 for formic acid. And now we can go ahead and plug in the information we have. Our pKa, 3.74, plus the log of our concentration of our base, 1.25 molarity, and then the concentration of our acid, 1.50 molarity. We would get a pH of 3.66. Now again, this is a buffer, and we are able to utilize the Henderson-Hasselbalch equation. But maybe if we wanted to connect this back to what we've done many times before, and thinking of, can we do this setting up a Rice table? So reaction, initial, change, and equilibrium. So again, we have our reaction. And a lot of times what we want to do is we want to take reactant 1 and reactant 2 and add them together. So we would think, oh, maybe it's just formic acid, potassium formate. But one thing that we want to observe with a buffer is that we do have the presence of a product for our acid ionization reaction of our formic acid. So for example, we're not going to look at that, but if we just look at the normal acid ionization reaction of formic acid, we're going to get H3O plus and the formate ion. So what this is telling us is that we actually start with some amount of our product and some amount of our reactant. So it's not necessarily that these two things are reacting together, but what we can say is that we have what we call this common ion that is present in our solution, which is going to cause our equilibrium to be shifted in a way that wouldn't be like that if we started with no potassium formate. So again, now we have our reaction. We want to write our initial change in equilibrium for those. So we start with 1.5 molarity of our formic acid. We start with 1.25 molarity of the formate ion, and we didn't directly add in any hydronium. Water is a pure liquid, so we don't include that in our K values and our expressions. Because we start with no H3O+, what that helps us identify is that must mean it's going to increase in concentration to get to equilibrium, and that means that our concentration of our reactant is going to decrease. So we end up with an expression for our reactants and our products here. Now, as we would always do now, is we're going to go ahead, right, and plug those into our Ka expression, right, these variables that we have for our reactants and products. So our Ka is going to be our product concentration divided by our reactant concentration at equilibrium. And we know the Ka value for our formic acid is 1.8 times 10 to the negative fourth. Again, we go to a table and we can find that. And we plug in what we have for our concentrations here. Now, if we look at this, we could plug in and we notice that we could solve for x. There's only one variable, but this is not an algebra class. We want to think, can we maybe simplify this a little bit? And we take a step back and we see we have a small K value here. And we're starting with a lot of product already, 1.25 molarity. And so what that lets us know is that we're not going to form that much more. So that tells us our X value is going to be small because we do have this small K value and we already start with a lot of product. So I could go ahead and see, can we make this assumption that these numbers of 1.25 and 1.5 are effectively going to be the same as if we included that minus X or if we didn't. And what that does is that simplifies our math to be 1.25x divided by 1.5 equals our K value. And now we can go ahead and solve for our X value, and we're going to get 2.16 times 10 to the negative fourth. And again, we say, okay, well, that's pretty small relative to our 1.25 or 1.5, so it makes sense that we can make that approximation. Now we go back to, we're trying to identify our pH. We know that that is our hydronium ion concentration. And so now, if we know our hydronium ion concentration, we can calculate our pH to be the negative log of that. And we would get a pH of, thankfully, the same pH that we originally got. So we notice we have the ability to choose either one of these. We could look at a Rice table, or we could use our Henderson-Hasselbalch equation to quantify our pH. I'm going to advocate for us to use this one because it simplifies it, but also we'll see when we deal with buffers and start to get more complicated buffers, it's easier to just simplify what we're looking at. And if you go into a biochem course, a lot of times this is the main way that they focus on calculating pH for a buffer.